Welcome to section 4.4, orthogonality. I'll try to share my enthusiasm with you about this stuff. I've declared this section simply awesome. What we're going to do is impose a sufficient number of conditions on a Hilbert space so that it behaves like Rn. The geometry of Rn will hold. The Gram-Schmidt process will play a role in this. We'll be able to talk about subspaces and orthogonal complements, or perp spaces, as the terms that we'll use here. And much of the benefit of Rn, in particular, the concept of a vector as having magnitude and direction, will legitimately hold in the appropriately restricted infinite dimensional Hilbert space. And we're working our way to the fundamental theorem of infinite dimensional vector spaces as well. So we'll start with taking advantage of the fact that a Hilbert space has an inner product and define vectors x and y in a Hilbert space H to be orthogonal if their inner product is 0. We'll denote that the usual way: x is perpendicular to y. And this is behavior very reminiscent of dot products and sophomore linear algebra and the vector space Rn or Cn. For any subset S, so a set this time, any subset of a Hilbert space will denote, I'll read this as S perp. It's called a perp set of set S, but S perp is the set of all vectors in H such that the inner product of x with S is 0 for all S vectors in set capital S. In other words, it's the set of all vectors perpendicular to everything in set S. And you can certainly visualize something geometric even in R3. We could take S to be the xy plane in R3 with the usual interpretation about vectors in standard position. And the perp space would be all vectors that point straight up or point straight down, all vectors perpendicular to the xy plane, all vectors parallel to the z-axis in a three-dimensional setting. So very geometric ideas, turns out quite useful as well. First proposition says, suppose S is a subset of a Hilbert space H, and suppose S is closed under scalar multiplication. So subset closed under scalar multiplication, not an assumption of subspace, but an assumption of subset closed under scalar multiplication. Then the claim is S perp, that is all X in H that are perpendicular to S, actually equals the set of vectors for which the distance from that vector X to set capital S is equal to the norm of the vector. So we described actually an idea of orthogonality back in the norm linear space setting, and we related distances to sets in terms of the norm of a vector. We defined orthogonal in the norm linear setting to be the distance from from vector X to set S is the norm of that vector. Possibly we did subspaces in that setting, but we didn't have this idea of inner products, and giving a formal orthogonal definition was not on the table back in norm linear spaces. We got further than you think we would have, having only norms. But this is reminiscent of that. And so the claim is really that this set of vectors given in the definition is equivalent to this set of vectors. Recall the distance from a vector or point to a set was defined in terms of an infimum. Let's look at the proof, and we'll see that infimum pretty early on. Okay. First, let's suppose the distance from X to S equals the norm of the vector. Then we want to show that that vector is in the perp space. So suppose the distance from X to S is the norm of vector X. Then for all vectors Y and S and any scalar t greater than 0, we've got closure under scalar multiplication, remember, we have the norm squared of X equals the distance squared. The distance is defined as the infimum of the norm of x minus y, where vector y ranges over set S, how we defined distance from a point to a set, from a vector to a set. We're using the terms point and vector interchangeably. I say regrettably somewhat, but we'll get by. Standard position allows us to resolve this in lots of settings. But this is the definition of the distance, so we'll get an equality there. It's an infimum, so let's compare it to the norm of x plus or minus t times y. We took t to be positive. We're going to split this into a couple of pieces. That's the reason the plus or minus thing appears here. But this is less than or equal to this norm because we're taking an infimum of vector x minus some element of s. Here we have vector x plus or minus some element of s. Ty is a vector in s, as is negative ty, to get the signs to balance there. But we're dealing with x minus an element, a specific element right here of set S. Well, this gives a specific norm of a vector. So that specific norm will be greater than or equal to the infimum of all such norms. The infimum is the smallest one, the least upper or the greatest lower bound. But the infimum will certainly be less than or equal to any specific element of the set. And whenever we take infima, it's always sets of real numbers. These are indeed sets of real numbers because they're norms of vectors. And this is just, two real numbers here with a plus or minus. But the norms give us real numbers and we take advantage. So we get an inequality here. This x plus or minus ty, norm squared, can be expressed as norm of the first squared plus norm of the second squared, an appropriate sign on sort of the cross terms. We've seen in the past in lemma 4.2, interpreting these inner products to be complex value, that what we get here is plus or minus respectively 2 times the real part of t times the inner product, or we could bring that t outside as well. Now, if we rearrange this, we can say we've got an inequality here. Norm x squared less than or equal to norm x squared, we could cancel those, plus t squared norm y squared plus or minus 2 times the real part of t times this inner product. So what we could do is take this to the other side of the equation, introducing a minus or plus a real part. Take the 2, divide, we'd get a t squared over 2. So I think we get a t over 2. It's a little bit of a typo here. We get a t over 2. The t would divide out as well. The t is positive, so we preserve the order, the inequality when dividing the t's out. But sorry, that should read t over 2. I will correct the notes. And from this, we can draw the conclusion, hey, this thing over here, the positive part is less than or equal to t over 2 times norm y squared. T could be anything greater than 0. In particular, t could be little. Well, if t is little, then we know the, say, the positive real part of this inner product must be less than or equal to 0. Take a limit as t approaches 0. And similarly, the negative real part of this inner product must be less than or equal to 0. Take a limit as t approaches 0. Well, the only way we can have the positive and the negative parts less than or equal to 0 is if the thing itself is 0. In other words, the real part of the inner product must equal 0. And we could do a similar analysis. Let's not get into the details, but we could take vector x plus or minus I ty. Same conditions, t is greater than 0. We'll just insert an I there. Not a problem. Scalars are complex in this chapter. And we've just got another element of set S. It times y is an element of set S. Set S was closed under scalar multiplication. And it is a scalar, complex scalar, I guess, because t is real. But not a problem. And we can iterate that same process, but a real part of x comma iy will appear. in that center term. But the real part of x times iy, use the property of inner products to bring the I out of the inner product, and that will produce a quantity equivalent to the imaginary part of the inner product. So we get the imaginary part of the inner product related to the real part of this thing here, and we get the same type of behavior. That is, we can draw the conclusion that the imaginary part of the inner product of x and y is also 0, similar to what we drew in a conclusion up here about the real part. So this allows us to do the same type of procedure, and we've just drawn the conclusion, I think fairly clearly for the real part and a little nebulously for the imaginary part with some details omitted. But hey, the real part and the imaginary part, they both 0. If they're both 0, then the inner product itself must be 0. That means these two vectors are orthogonal. So we started this under the assumption that the distance from x to s was equal to the norm of s. That is, this condition is satisfied for vector x. And we've shown that that implies s is in S perp. So what we've really shown is this set is a subset of S perp. The vectors x such that the distance from x to s equals the norm is a subset of S perp. We want to show equality, so next slide, we'll reverse that subset inclusion. Conversely, suppose we choose something in S perp. Then for every y in S, if we look at the norm of x minus y squared, expand that out using the definition of norm squared, it produces this. We have assumed x is in S perp. That means the inner product is 0. So this term is 0. We can drop that. This simplifies to norm x squared plus norm y squared. Certainly that's greater than or equal to the norm of x squared because the norm of y squared is greater than or equal to 0. So just drop that. And whoops. And that establishes this inequality. So we've got the distance from x to s also bounded below by this quantity. Now that's because what we're going to do, we take square roots first to get the squares out of the way, but we've got the norm of x minus y greater than or equal to the norm of x. We'll define the distance from x to s by taking an infimum over all y, right? The y was chosen from set S. This is how you define the distance from x to s. Here's another restatement of it here. We'll take an infimum over all y in S. So do that here. Take an infimum over all y. Well, these are always bounded below by the norm of x, if you get the squares out of the way. So when you take the infimum, it's also got that lower bound of norm of x, an infimum over the y's. It's the y's that vary, the x is fixed. So we can conclude that the distance from x to s is greater than or equal to the norm of x. By that, we're actually trying to show the equality, so it looks like we're halfway there with that. Now, 0 is in S. S is closed under scalar multiplication, so take something in S and multiply it by the 0 scalar, and that produces the 0 vector. We haven't assumed S was a subspace. And if it is a subspace, it satisfies the hypotheses here. I mean, we're more probably prone to deal with this with subspaces more than subsets, but it's stated in a general form. But we know the 0 vector is in S. So when we take this infimum, the infimum must be less than or equal to whatever we get by choosing a particular y in S. Well, let's choose a 0 vector. That produces x minus 0 norm of, which is simply the norm of x. And above, we had that distance bounded below by the norm of x. So we've got the norm of x less than or equal to the distance, less than or equal to the norm of x. Well, those less thans or equals must actually be equals, since we've got the same thing on the far left and the far right, namely the norm of x. And we must have that the distance from x to s actually equals the norm of x. So there's the other part. That is, this x value is in this set. We chose in this slide x to be an arbitrary element of S perp, And we showed X is in that set on the right-hand side. So we've shown this is a subset of that. S perp is a subset of the set on the right. The previous slide, we had that subset inclusion reversed. So there's your set equality as claimed. Back to the notes. Okay, so this gives us a little alternate classification of how to describe the S perp collections of vectors. An exercise I made up just to justify this following claim. I made it up, you can tell, because it's got not a number, but a letter is its name. Exercise 4.A, I'll call it. Says for any set S in a Hilbert space H, the set S perp is a closed subspace of H, so topologically closed. Also, we're extracting the fact that we're dealing with a subspace here. Follows fairly easily from properties, the linearity properties of inner products. So it's a straightforward exercise to establish this. So perp spaces are closed subspaces. I bring that up because the next theorem deals with M, a closed subspace of a Hilbert space. So an example of M would be a perp space for a given set. So let M be a closed subspace of a Hilbert space H, then M intersect M perp is a zero vector. Not too surprising. We'll put together a little one-line argument to justify it, though. Secondly, if we choose any vector in H, call it Z, this can be written uniquely as a sum of an element of M and an element of M perp. That is, we can take Z and write it as the projection of Z onto M plus the projection of Z onto M perp. Very reminiscent of the Gram-Schmidt process. Also, there's a uniqueness going on here. So this is very much related to the Gram-Schmidt process. Thirdly, M perp perp, the perp set of the perp space of the closed subspace is M itself. That makes pretty good geometric sense as well. We do need to have a subspace to have this occur. If I dealt with sets, this wouldn't quite work out entirely correctly. But with subspaces, we get M perp perp equals M. And finally, H is isometric to the direct sum of M and M perp, where the direct sum is equipped with the L2 norm. Gee, there's L2 again. L2 is going to play a big role before we're done in this section. So let's go through the proof of those four claims. Let's take care of this first one. Hey, if X is in both M and M perp, then the inner product of X with itself is zero, because anything in this space is perpendicular to anything in that space. If X is in both of them, the inner product of X with itself must be zero. But we're dealing with an inner product, not a semi-inner product. And the only time this occurs is when X is a zero vector. And there's part A. So easy enough. Like in part B, very geometric. We're going to sort of intertwine the proofs of B and C. That's why I've left the statements of both of them here. We'll prove half of part B, then we'll prove part C, and then we'll finish up the uniqueness claim in part B. So to address part B, let's take Z to be an arbitrary vector in the Hilbert space H. Let's define Y to be Z minus the projection onto subspace M of Z. What we want to show is this quantity is the projection onto the perp space of M of Z, so that we can get this equation established. We want to show Y equals this, in other words. Now the projection onto M of Z is the vector in M nearest Z. We define these projections I think at the end of the previous section. In other words, this projection would involve an infimum of norm of Z minus M, where M ranges over the subspace capital M. So vector nearest z, by the way, we know such a vector exists from some results from the previous section. Letting M range over capital M, and this was, by definition, the projection onto M of Z. So this gives us a norm of Z times the projection onto M of Z. Now, for any vector M in the subspace, so we're letting that vary now, we have norm of Y minus M, or Y we've defined up here. Here's a definition of Y. The norm of Z minus the projection onto M of Z minus M. Substitution, rearrange, that's Z minus this stuff here. Hey, both of these are vectors in capital M. This is a projection of Z onto capital M, which is an element of capital M, and M itself is in capital M. So over here we have an element of subspace M. So this quantity would be greater than or equal to the infimum of Z minus elements of M. Usual thing, here we're taking an infimum, think of it as the smallest such of these, and this is one of these. Well, the smallest one is less than or equal to one of them. To be informal, but a property of infima. And as we saw, then this infimum is the way we define projections. This is the norm of Z minus p sub M of Z, this quantity here, the infimum of this quantity here is Z minus the projection onto M of Z. And that quantity there, or that vector there, was by definition Y. We introduced Y to denote that. So what we've got here is the norm of Y minus M is greater than or equal to the norm of Y itself, where M was an arbitrary element of capital M, the subspace. So if we take an infimum over all such M, for the elements of that set, the real numbers in this set, norm of Y minus M, they're each greater than or equal to the norm of Y. So the infimum will be greater than or equal to norm of Y. The infimum also by definition is the distance from Y to M. So we've shown the distance from Y to M now is greater than or equal to the norm of Y. Similar to what we did previously, the zero vector is in M. So this lower bound is actually attained when we set little m equal to the zero vector. Zero vectors in M, right? Right, it's a subspace. It's a vector space itself, so it contains a zero vector. We did a similar argument in the previous proof dealing with closure under scalar multiplications. But here we're taking advantage of the fact that M is a subspace. So that distance is attained, and the distance from Y to M actually equals the norm of Y. Well, we just said that's another way to describe the perp set. In this case, the perp space. Vectors satisfying this, we said in proposition 4.13, were vectors in the perp space of this space. We dealt with it in terms of sets closed under scalar multiplication, but capital M is a set closed under scalar multiplication. I told you we were probably going to use it on subspaces. So this Y vector must be in the perp space. That is, this vector Z minus the projection onto M of Z must be in the perp space. All right, we're trying to get to this representation. I think we're pretty close. So we'll take Z. We wrote it as the projection plus Y. Here we go. We had, let me go back. We had Y equals Z minus the projection onto M. So we can take Z and write it as Y plus that projection. So what we've done, yeah, there we go. Z is Y plus that projection, and this is the Y parameter here. So we just rearrange the very definition of the symbols of Y. And we showed that that Y was in the perp space. So we've got the projection of Z onto M. That's an element of capital M, by the way we define projections. And Y, that is the Z minus projection onto M of Z. We showed on the previous slide that's M perp. So Z was arbitrary. It can be written as a sum of an element of M and an element of M perp. Part B says every vector in H can be written uniquely as a sum of an element of M and an element of M perp. Well, here's one way to do it. So we just showed we get this type of behavior here. So we have Z written as an element of M and an element of M perp. This thing here, which we're denoting up here, is a projection onto M perp of Z. What's missing is the uniqueness stuff, so we have to come back and deal with that. Part C says the perp space of the perp space is the space itself, M perp perp, M double perp equals capital M. Well, M perp is a set of all vectors in H that are orthogonal to subspace M. M perp perp is a set of all vectors orthogonal to M perp. Well, that includes all the vectors in M. So we immediately have M as a subspace of M perp perp. Maybe pause the video and ponder on that. It's not very profound, but it might take a second to sink in. And we're halfway there. We just need to reverse that inequality, or I'm sorry, that subset inclusion. So suppose we take Z to be in M perp perp. Then Z is an element of H because all these things are subspaces, I guess in this case, certainly subsets of the Hilbert space capital H. We just saw that we can take Z and write it as X plus Y for some X in capital M and some Y in M perp. Part B. There exists such a representation. We know M itself is a subspace of M perp perp, as argued above. So let's see, X is in M, so X is in M perp perp, and Y, Z minus X, is also in M perp perp. X is in M perp perp, and Z is in M perp perp. M perp perp, we stated upstairs in that, when we reference that exercise, that these perp spaces are themselves subspaces. So we get the closure under linearity. So we can show the vector Z minus X, let's call it Y, is in M perp perp. Yeah, closed under linear combinations. So if Y is in M perp perp, oh, excuse me, we had this relationship. Sorry, I wasn't defining Y there. I'm rearranging this relationship. And we had chosen Y up there to be an M perp. So we see Y is an M perp by above, and Y is an M perp perp. Y is an M perp perp. Part A tells us the only thing that's in a space and its perp space is a zero vector. That was part A. M intersect M perp is a zero vector. Same basic idea here. We got an extra perp going on, but same idea. So it must be that this Y being in both the M perp as given here and M perp perp as shown here tells us that Y vector must be the zero vector. That Y vector is Z minus X. So Z minus X must be the zero vector, or Z and X must be equal. And in M, let's see, X is in M. So there's that property. And so Z is in M as well. And we've shown M perp perp is a subset of M because we chose Z to be an arbitrary element of M perp perp and showed that Z is also in M. In other words, from the set theoretic argument, this kind of subset inclusion, we got the subset inclusion going one direction here, the other direction there, and there's the set equality, and there's part C. So M perp perp equals M. Warning one last time, M's not just a set. it's a subspace. So the subspace stuff matters in this conclusion. So to complete part B, we need to show the uniqueness part. So suppose we can write Z in two different ways. Say Z equals X1 plus Y1 and Z equals X2 plus Y2, where the X's are from M and the Y's are from M perp. So this would represent two kinds of linear combinations, two kinds of sums that produce Z using an element of M and an element of M perp, using an element of M and an element of M perp. Then we can take this part of the equality, rearrange it, take the X2 to one side and the Y1 to the other side, and we'll get X1 minus X2 equals Y2 minus Y1. But X1 minus X2, both of those are in M, it's a subspace, so that vector difference is in M. Y2 minus Y1, both of the Y's are in M perp, so that difference is also in M perp. These two vectors are equal, and that resulting vector is also, or is in M and also in M perp, but the only thing in M and M perp is a zero vector. So it must be this equals the zero vector, applying part A there to draw the zero vector conclusion. Hey, if you got the zero vector, then it must be X1 equals X2 and Y1 equals Y2. And so the representation of Z as a sum of an element of M and an element of M perp must be unique. What we did on the previous slide, we had a projection and we had something else. We haven't really shown the something else must be the projection of Z onto M perp. So we need to establish that. So using the same technique we had on the previous page, except adding an extra perp, we're going to replace the closed subspace M with a closed subspace M perp. And so we'll replace the closed subspace above M perp with the subspace M perp perp in these comments. So we're adding an extra perp, if you like. We had, well, we certainly have Z as projection onto M perp of Z plus Z minus that projection because these cancel. So that's a straightforward equality. And Z minus the projection of M, projection of Z onto M perp. All right, we're taking away, think of it, taking away the component of Z in the M perp direction. So what you're left with would be a vector in M perp perp. Like I said, we'd have perp spaces and perp perp spaces in this little conversation. But hey, the perp perp space is the same as the original space. That's what part C said. So this Z minus the projection of M onto the perp space of Z actually must be an element of M. You know, we've got a uniqueness of the representation. So this thing here must actually be the projection of M, the projection of Z onto M. So this, being an element of M, must be the projection, and so that ties it together, and we get Z written as this type of linear combination, and there's part B. So unique linear combination. In fact, it's written as a sum of two projections. Well, the sum of a projection and a projection onto a perp space. An orthogonal complement is what we get. We haven't introduced those words yet, but that's probably words you've encountered before. And there was a final part to this. I can get my slides to advance. Excuse me briefly. There we go. Final part to this, part D. H is isometric to the direct sum of M and M perp, where the direct sum is equipped with the L2 norm. Okay. Direct sum, and this is going to produce ordered pairs, an element of M and an element of M perp. And hey, we just showed any vector in H can be written as a linear combination of a vector here in M and a vector there in M perp. So define pi mapping H into the direct sum as pi of Z equals the projection of Z onto M, comma, the projection of Z onto M perp. By the way, you know that Z is the sum of these two, and they're uniquely, that's the unique way to represent Z, as a sum of an element here and an element there. Quote unquote, clearly, use that with a grain of salt. Pi's 1 to 1, yeah, that's where the uniqueness thing comes in. So we get a 1 to 1 mapping here. It's onto everything, and H can be expressed in terms of a combination like this. So that takes care of the onto-ness. Preserves linear combinations. That should be fairly straightforward with the way we define the projections. And so we have a linear transformation that's also a bijection. Then we have a linear space isomorphism. Now that's not all we're trying to show. We're trying to show isometry. So we have a linear space isomorphism. We need to show distances are the same. So we need to have a conversation about the norm. None of this stuff in this sentence here addresses the norm. It only addresses the linear space structure. But if we take Z and H, you want to find the projection of Z, the 2 norm of that. Said we were going to equip the direct sum with a 2 norm. Let's take that 2 norm squared. Pi of Z by definition is this ordered pair here. 2 norm squared, right? The subscript indicates we're using the little L2 norm. The superscript indicates, well, it's not a superscript, it's an exponent. So we're squaring is what the exponents are. The 2 norm would say, we'll take the norm of this, square it, norm of the first one squared, plus norm of the second one squared, square root of. Well, the square root vanishes with the squaring here. And so we get a norm of the projection onto M squared, norm of the projection onto M perp squared. So now we're actually using the norm in space H. When we go to this setting, we've got that, let's see, this equals the norm of Z, lemma 4.2. I don't quite remember lemma 4.2 right now, but if you'll take the norm of Z, hey, you know Z can be written as this plus that. The norm is induced by the inner product, so we could take the inner product of P sub M of Z plus P sub M perp of Z. I mean, that is Z itself, as we saw previously. So take the inner product of that, the sum of those two with itself. You'll get a first term squared, in a sense, a last term squared, and the center term will involve the inner product of the projection onto M and the projection onto M perp. And its center term will be 0 because of the orthogonality behavior. And so that allows us to draw the conclusion that we get norm Z squared here. And so indeed, we took the arbitrary vector, I guess start on this side, an arbitrary vector Z in H, and we saw that pi of Z, its image in this direct sum space, has the same norm. Okay, they're both squared. I take square roots, I lose the exponents. I keep the 2 here because it indicates the L2 norm. But we'll have the norms be the same in those 2 spaces. That is, we have an isometry. So this ain't the last time we'll see relationships between Hilbert spaces in the space little L2. Back to the notes. Okay. I want to do something with bases. I'm going to introduce some supplemental material and provide videos on the supplements instead of doing it both in this setting and the other setting. But the details of much of what follows can be found in the supplement related to these 2 sections of the Hong, Wang, and Gardner book. And there's videos prepared for those. First, if X sub k is an orthonormal sequence, Okay, so it's a bunch of unit vectors, and they're all orthogonal. Inner product is 0 between any pair of distinct such vertices, for which the closed linear span of that set is all of Hilbert space H. That is, take all possible linear combinations, finite linear combinations, and close that topologically. So take the closure of that. Then X sub k is an ordered orthonormal basis of H. So here's what we mean by orthonormal basis of H. It's a little bit more, this closure thing is going to play a certain role. We're still talking about taking finite linear combinations here. I want to say Hamel basis. Yeah, I want to say Hamel basis in this setting. We're not interested in Hamel bases. We're interested in Schauder bases. All right, to do what we need to do, we need to step aside and or go through the same stuff twice. But let's just borrow from real analysis with an introduction to wavelets and applications. Really, I just need the stuff from the chapter on Hilbert spaces. I co-authored this thing. I wrote the chapter on Hilbert spaces, so that's my favorite chapter. But we need some results from section 5.1, which basically just set up vector spaces. We need some results concerning Hilbert space isomorphisms as well. So I'll just run through statements of those, quite possibly in the order you're going through the videos. We've already done the 5.1 stuff, but Theorem 5.1.4 says vector space VF. So we're taking the scalar field to be any old field in this particular result. There exists a set of vectors B such that B is linearly independent, and any vector V is some linear combination of those vectors in that set B. In other words, that set B is a Hamel basis. So Theorem 5.1.4 says every vector space has a basis, where basis is defined in the sense used in sophomore linear algebra, always with finite linear combinations. An exercise that we went through in that section as well says if we have two bases for a given infinite dimensional vector space, they have the same cardinality, two Hamel bases. Not surprising, you do that in sophomore linear algebra. Well, you don't do that. You do that for finite dimensional, not infinite dimensional spaces. And Hamel basis is no big concern in finite dimensions. But I don't like Hamel bases in these other spaces. To show they exist, to show the previous comment, you need the axiom of choice. And we're going to go through that stuff again as well. Zorn's lemma is what you need, which is equivalent to the axiom of choice. Theorem 5.4.4 says a Hilbert space with a Schauder basis has an orthonormal basis. Schauder basis was a countable basis. So these countable bases, you can simply apply the Gram-Schmidt process to produce a Schauder orthonormal basis. Theorem 5.4.8, a Hilbert space with scalar field R or C is separable if and only if it has a countable orthonormal basis. So these ideas of separability and the existence of a countable orthonormal basis, these two ideas in the end go hand in hand. You read different functional analysis books, and they will be all interested in separable Hilbert spaces over the reals or the complexes. I say, no, they ain't. They're interested in Hilbert spaces with countable orthonormal bases. They're not interested in separable Hilbert spaces. Well, beyond the fact that that turns out to be equivalent things. But it's not the separability. Remember, separable meant countable dense subset. That ain't the thing you're interested in. It turns out that's a thing that's related to, if and only if, the thing you are interested in, I say, having a countable orthonormal basis. And here's where we're stuck so far. We don't know how to find these bases just yet. Hamel bases, we got no clue how to find Hamel bases. We'll have a way to find bases of this sort, countable orthonormal bases, orthonormal Schauder bases. We'll have a way to find these. The fundamental theorem of infinite dimensional vector spaces says, and this is merely a statement of it, we'll go through it in great detail in the supplements, says let H be a Hilbert space with a countable infinite orthonormal basis. Okay, I need to be a little more clear. Here, we're talking about a basis in the sense of Schauder. That is, we're allowing infinite linear combinations here. That's not immediate from the statement, but it's laid out in that context in the supplement. Then H is isomorphic to L2. So I said in the past, we had a fundamental theorem of finite dimensional vector spaces. You give me the scalar field and the dimension, I'll tell you the vector space. And I said we'll have a fundamental theorem of infinite dimensional vector spaces, which would guarantee, if we're dealing with an infinite dimensional vector space with a layer of details, then I can tell you what that vector space is. So it's still a classification theorem. I'm telling you, up to isomorphism, what an infinite dimensional vector space with some added details looks like. It's isomorphic to little l2. Well, now we can be a little clearer on what that layer of details is. We require that Hilbert space to have a countable infinite orthonormal basis, where, when I say basis, I'm allowing infinite linear combinations. Yeah, we can do that as long as we have a norm. And in a Hilbert space, we've got an inner product that induces a norm. But again, here we're allowing infinite linear combinations. Somewhat misleading terminology. Up here, Promislow is not allowing, not yet, infinite linear combinations. They talk about linear span, they mean finite linear spans up there. That's why they have to throw a topological closure in on what they're doing here. Some properties of orthonormal sets. Also, this is from section 5.4, the supplemental material. Let X sub I be an orthonormal sequence in a Hilbert space H, and let M be the closed linear span of the elements of this sequence. Finite. But they're taking the closure of that finite linear span. Given a sequence alpha, that is alpha sub I, of scalars, we'll take them to be complex numbers, the sum from 1 to infinity of alpha sub I times X sub I converges to some element X in the Hilbert space if and only if that sequence of coefficients is in little l2. In that case, the norm of X in the Hilbert space equals the L2 norm of the sequence alpha. So this very closely ties together these kinds of things with elements of L2. These series, so here we're making a transition, talking about infinite linear sums, talking about series. We get these series to converge if and only if the coefficients, the sequence of coefficients, is an element of little l2. That is, the sequence of coefficients is square summable. There's L2 again, not a coincidence. In addition, for any z, a vector in the Hilbert space, the projection onto M of z, M was the closed linear span of this collection of orthonormal vectors, this sequence of orthonormal vectors. The projection onto M can be written as one of these series as well. So I leave it to the supplement in section 5.4 from the Hong, Wang, and Gardner book on projections in Hilbert spaces to establish these details. But we'll take those as given. And what we want to show is every Hilbert space has an orthonormal basis. We'll use some of these results up here. Before we go through a proof of this, and we're using the term orthonormal basis back in the setting of Promislow, make a statement about that. Yeah, we return to Promislow's terminology on this. We're using the idea of an orthonormal basis as stated in Promislow, orthonormal basis, where we're taking finite linear combinations. The closure will allow us to deal with series, and when we say orthonormal basis, it has specifically this particular definition, but we're not to the point where we have all the nice geometry of Rn just yet. Having an orthonormal basis is not what we need. We need a countable orthonormal basis. We need to be able to write these in terms of series, not in terms of finite sums. Before we give a proof of 4.18, we need to go through some set theory stuff. We actually went through this whenever we showed that every vector space has a Hamel basis. That would have been in the supplemental material as well. So we're going to rehash that, so I won't dwell on it, but let's step aside and do some set theory for a few minutes. For set X, any subset of the Cartesian product of X with itself is called a binary relation, or simply a relation, binary because there are two of them. A relation R on X is said to be reflexive if, for all X, we have the ordered pair X comma X in the relation. In other words, X is related to itself. That's what reflexive means. R is symmetric if, let me read it in terms of is related to instead of ordered pairs. Symmetric if X is related to Y implies Y is related to X. Transitive if X related to Y and Y related to Z implies X is related to Z. Usual ideas of transitivity. Definition of a binary relation, or simply a relation. A relation is an equivalence relation if it's reflexive, symmetric, and transitive. A relation's anti-symmetric if X related to Y and Y related to X implies that X equals Y. So I'm very much thinking like maybe subset inclusion would be an example of an anti-symmetric relation. We'll use subset inclusion fairly often, and well, in the thing we need upcoming. Less than or equal to if we were dealing with real numbers. There's an idea if X is less than or equal to Y and Y is less than or equal to X, they must be equal to each other. But there's some examples of anti-symmetric. A relation is a partial ordering if it's reflexive, anti-symmetric, and transitive, and we'll denote partial orderings using these symbols here. In the Hong-Wang-Gardner book, we use slightly different symbols, but this is the symbols used by Promislow, so we'll stick with those. R is a total ordering if it's a partial ordering, and for any X and Y, we have either X is related to Y, say X is less than or equal to Y, I'll read it as, or Y is less than or equal to X. The idea of a total ordering is any two vectors are comparable. And I might have a partial ordering where X and Y, we don't have X related to Y, nor do we have Y related to X. They're just not comparable. Comparable is my term. In a total ordering, we have any pair of vertices. One is related to the other. So either X is less than or equal to Y, or Y is less than or equal to X, using the notation of partial orderings. If set X is partially ordered by this relation, a maximal element of X is such that X is less than or equal to Y implies Y equals X. So an element is maximal if there's nothing greater than or equal to it. That is, if we take something greater than or equal to it, it must be that X value itself. So there's nothing greater than or equal to X means it's a maximal element. Hey, if we're in a partial ordering, there might be some other stuff that's not even comparable to it. So I can't address, which way the inequality goes if it's only a partial ordering. And minimal element X is minimal if Y less than or equal to X also implies Y equals X. That is, there's nothing else less than X. Means X is a minimal element. If E is a subset of X, an upper bound for E is an element X of, I want to think of them as vectors, I guess they're just set elements, such that Y is less than or equal to X for all Y and E. So this requires not only that X be comparable to all of the elements of set E, but that they satisfy this relationship. The following result is equivalent to the axiom of choice, unfortunately. Zorn's lemma, equivalent to the axiom of choice, talks about these partial orderings and maximal elements and all that stuff, which is why we went through those definitions. We don't really, functional analysis class need really a lot of hands-on experience with this stuff, but we're making a big claim, so we ought to go through and justify it. And the necessary evil is the equipment of set theory and Zorn's lemma. If X is a partially ordered set and every totally ordered subset of X has an upper bound, then X has a maximal element. All right, we were talking about orthonormal bases. That maximal element is going to be an orthonormal basis. So we're ready to go through and prove 4.18, and we'll use Zorn's lemma. And we'll make some derogatory commentary following the proof about what's wrong with that. Okay, every Hilbert space has an orthonormal basis in the sense defined by Promeslip. So this is only a slide long, but it's a pretty busy slide. Let P be the class whose members are all orthonormal subsets of Hilbert space H. And define the partial order. I'll read it as less than or equal to, it's just a partial ordering, on this class of sets as A less than or equal to B means A is a subset of B. So it's orthonormal sets of vectors, so it makes sense to talk about one being a subset of another. It's a partial ordering because I could have orthonormal sets of vectors where neither is a subset of the other. So it's a partial ordering, so we're okay. For any non-zero vector X in the Hilbert space, we can take that vector and normalize it, and that set consisting of this single unit vector, uninteresting, but it is an orthonormal set. It's orthogonal to everything in the set other than itself, because there's nothing in the set other than itself, and it's a unit vector. So this allows us to draw the important conclusion that, by the way, P is non-empty. So this class of sets is non-empty. Suppose Q is a completely ordered subset of P. If we can show Q has an upper bound, then we will have shown that an arbitrary, completely ordered subset of P has an upper bound. And then we can use Zorn's lemma. Define C to be the union of all of the sets in Q. So we're unioning together a bunch of orthonormal sets. Those sets are nested. Completely ordered subset. So we got a bunch of sets, and I kind of want to, well, nested is not the best word, but I want to think of them. This one is a subset of that one, is a subset of that one, is a subset of that one. Now that I don't want to necessarily think countable for one thing, because nobody's put those kind of constraints on anything. But think of them sort of like they're nested. So if we'll take the union of all those sets, that will create itself an orthonormal set. And so C itself must be an element of P. P was a class of all orthonormal sets. So C is an upper bound of Q. We took an arbitrary, completely ordered subset and showed that it has an upper bound. Let's take a real quick look at Zorn's lemma. Zorn's lemma says every totally ordered subset has an upper bound. That's exactly what we did. That's what Q was. Q is a completely ordered subset, and it has a maximal element. An upper bound. Then Zorn's lemma tells us P has a maximal element. Call it D. D will be the desired orthonormal basis. D's in P, when it's a maximal element of P, so it's contained in P. P is a collection of orthonormal sets, so D itself is an orthonormal set. Consider the closed linear span M of D. We want to show M equals H. And that, according to Promislow's approach to an orthonormal basis, will show us that D is an orthonormal basis. But we've taken this extra little shift here of going to the closed linear span. And again, linear is meaning finite linear combinations. The closure is kind of throwing in limit points. If there's an X in the Hilbert space that's not in that closed linear span, X is not in M, then we can take X and write it as its projection onto M plus its projection onto M perp. Projection theorem lets you do that for any subset of the Hilbert space that's closed under scalar multiplication. I think that's what we needed for the projection theorem. Well, we've got that. It involves a linear span. So we've got closure under the appropriate stuff. So we can take X and write it as the sum of these two projections. The projection onto M perp would have to be non-zero, or else X would be an element of M itself. But then we can take this projection of X onto M perp, being the non-zero vector, and we can normalize it and make it a unit vector. That's going to be perpendicular to everything in M. So here's a new vector, not contained in D, because when we took all linear combinations of D and some closure, that produced M. So we found a vector that's perpendicular to all the vectors in D. The vectors in D, in a sense, generate subspace M, and we found something perpendicular to that. We're very much using a magnitude and direction, well, a direction idea in this. So we found a new direction. If X isn't in that little subspace, there's a piece of it that sticks up out of that subspace M. Sticks, I don't know, straight out because of the orthogonality, but this points in what I'd call a fundamentally new direction. Well, normalize it, make it a unit vector, and it'll be perpendicular to everything else. Wait, you can't do that. Here, we've taken D, we've added a unit vector to it that's orthogonal to everything in D. But then, this is an orthonormal set. That's the reason we normalize that little direction. And it strictly contains D. Here we've got a bigger set that's also an orthonormal set. Well, it's a contradiction because D was, where is it? D is an upper bound. Upper bound Q. No, sorry, a maximal element. You can't find something bigger. We made an assumption. There's X and H that's not in M, and we got a contradiction. We found a bigger set, bigger than the maximal element. Contradiction, the maximality. What's wrong is the assumption we made here. There must not be such an X, so all X in the Hilbert space must actually be in M, must be in that closed linear span of the orthonormal set D. That means, by the definition, that D is an orthonormal basis for H. So that's the last proof. Let's complain about that, because that's my job. All right, you like this? We showed there exists an orthonormal basis in the sense defined by Promislow for any Hilbert space. I can't emphasize enough, this involves finite linear combinations. Yeah, but it takes Zorn's lemma to find this thing. That means you got no idea what's in it. Zorn's lemma guarantees the existence of this orthonormal basis without actually showing you how to find it. Just the same problem we had with Hamel bases. Every vector space has a Hamel basis. Yeah, but I don't know how to find them. I don't know what's in them because I know they exist by Zorn's lemma. Zorn's lemma guarantees the existence of something. It guarantees the existence of a maximal element. The axiom of choice guarantees something. It guarantees a set created using something called a choice function. That's the reason it's called the axiom of choice. But all these things guarantee the existence of something without showing you how to find it. So this is not useful stuff. I know the things are out there, but I don't know how to find them. So not very useful for applications. These orthonormal things exist, but I don't know how to find them. We need to go further. We need Schauder. We need to do this in the sense of Schauder. We want a countable orthonormal Schauder basis. We want to take infinite linear combinations. That fixes everything. Promislow at this stage is still stuck in the realm of finite linear combinations, followed by closure. We can find an orthonormal basis that behaves in that way, but I don't know what's in it because it takes Zorn's lemma to guarantee the existence of it. So we're going to go a little different direction and consider Hilbert spaces that are separable, have a countable dense subset. That changes everything. That ultimately guarantees the nice kind of orthonormal basis. And we'll take linear combinations using infinite linear combinations, using series. And that fixes everything. And that gives us the fundamental theorem of infinite dimensional vector spaces. Theorem 419 says any separable infinite dimensional Hilbert space is isomorphic to L2. Here's the new hypothesis there. We need infinite dimensional. If it's finite dimensional, you know what it's isomorphic to. It's isomorphic to, I don't know, Rn or Cn, scalar field N. So this actually, Promislow's 4.19, this is what I would call the fundamental theorem of infinite dimensional vector spaces. So it's the separability that lets you make the transition in such a way that you're guaranteed to get only one infinite dimensional separable Hilbert space because all such spaces are isomorphic. They're isomorphic to L2 and hence isomorphic to each other. So that's why you like little L2. The Graham-Schmidt process, Promislow's theorem 420 says, given a linearly independent sequence y sub k in a Hilbert space H, there's an orthonormal sequence x sub k. So we take the y sub k's and turn them into x sub k's such that the span of the first n of those vectors x equals the span of the first n of those vectors y, and that works for all n. So span, and they're only taking finite collections of vectors. So they're taking all linear combinations of these finite collections of vectors. I really want to do infinite sums, infinite linear combinations. But this is your pal, the Graham-Schmidt process from linear algebra. All right, it's done in a Hilbert space. It's done for arbitrarily large, right, for any natural number, arbitrarily large collections of vectors, but not for infinite collections of vectors. Well, this is something I guess you could prove by induction. This is a claim that holds for all natural numbers n. But that doesn't mean it holds for infinite collections. It holds for finite collections, no matter how big you want to make them, but finite. Turns out this holds in infinite dimensional spaces, and it allows us to create an orthonormal Schauder basis in an infinite dimensional Hilbert space with a countable basis. I think I probably need to throw the word separable in there as well. It allows us to do this in a separable Hilbert space. So in separable Hilbert spaces, we can find Schauder bases, and we can build them, and we can see what they are, and we can interpret vectors as magnitude and direction. That's where you can get some applications done. So all this stuff boils down to, I want to do something like I do in Rn, but do it in infinite dimensions. What are you going to worry about? Well, divergence when you pass to the infinite. So with the appropriate cleaning up of the details, we end up in the space little L2, and we can do all that geometric stuff you do in Rn. So it's worth the trip. Theorem 4.21 says if S is an orthonormal set in any separable Hilbert space H, then S is either finite or countably infinite. this leads us ultimately to Schauder bases. Hey, finite, well, if you take the span of that, you're going to get a finite dimensional vector space. Countably infinite, if you take the span of that the way I want to take spans, with infinite linear combinations, this can ultimately lead to the Schauder basis stuff. And this is dealt with as well in Theorem 5.4.8 of Hong, Wang, and Gardner. So next, actually probably what we'll do is step into the section 5.4 in that supplemental reference and go through some of these claims we made in this section in more detail. I will see you there. Have a nice day.